How big can anything really be? A single galaxy holds hundreds of billions of stars, each with its own planets. Yet even that galaxy is just a tiny fragment of the universe's true scale. Stars cluster into galaxies, galaxies into groups, groups into superclusters, and superclusters stretch across cosmic voids so vast that light, traveling at 300 million meters per second, takes billions of years to cross them. The largest known structures, like the Hercules-Corona Borealis Great Wall, span over 10 billion light-years, distances beyond comprehension. We start with what surrounds you, the mountains, oceans and continents of Earth. Then we ascend step by step to the moon, through our solar system, past the sun, to nearby stars, our galaxy of 400 billion suns, neighboring galaxies, and finally the largest cosmic structures ever observed. Each step comes with clear measurements and comparisons to help you visualize these unimaginable scales. By the end, you'll see how a single grain of sand compares to the observable universe, and why the gap between a human and the edge of everything is as vast as the distance from the Planck length to a single human cell, only in reverse. This is episode 2 of 2, The Giant Universe Beyond Us. Let's journey from human to cosmic, from the familiar to the incomprehensible, from Earth to the edge of the observable universe. Right now, as you experience these words, you exist at what we call the human scale. This represents far more than just your physical height of roughly 1.7 meters. Human scale defines the fundamental frame of reference through which we perceive and measure everything else in the universe. Understanding the significance of human scale requires recognizing that it emerges from deep physical principles. Your height results from the size of carbon atoms, the strength of molecular bonds, the efficiency of cellular metabolism, and the mechanics of structural engineering in biological materials. These factors converge to create body plans that typically range between 1 and 2 meters for large terrestrial organisms. This scale represents the intersection where quantum mechanical effects become negligible and classical physics dominates our direct experience. At human dimensions, we don't observe wave-particle duality, quantum tunneling, or uncertainty principles in our daily interactions. Instead, we experience the familiar world of solid objects, predictable motion, and classical cause and effect. Yet human scale also provides the perfect vantage point for scientific investigation. We're large enough to build instruments that probe smaller scales while remaining small enough to study astronomical phenomena without being overwhelmed by cosmic forces. This intermediate position has enabled our species to discover both quantum mechanics and cosmology. Your 1.7-meter height contains approximately 37 trillion cells, each measuring about 10 micrometers across. These cells integrate their activities to create tissues, organs, and the complete biological system that generates your consciousness. The emergence of awareness from cellular components represents one of the most remarkable phenomena in the natural world. Consider the mathematical relationships that define human proportions. Your arm span roughly equals your height. Your foot length approximates 1/7 of your height. These proportional relationships reflect optimal engineering solutions for bipedal locomotion and tool manipulation that our species developed over millions of years of evolution. Human sensory capabilities define our natural observational limits. Your eyes detect electromagnetic radiation in wavelengths between 380 and 750 nanometers, what we call visible light. Your ears respond to sound waves between roughly 20 and 20,000 hertz. Your nervous system processes information at speeds measured in meters per second rather than the light speed that governs electromagnetic phenomena. These sensory limitations shaped human intuition about the natural world. We naturally think in terms of solid objects moving through empty space at reasonable speeds according to predictable laws. This intuitive physics works perfectly at human scale, but breaks down completely when applied to quantum mechanics or relativistic phenomena. The energy scale of human experience centers around chemical energy stored in molecular bonds. Your metabolism operates at roughly 100 watts, similar to a bright light bulb. This energy level allows for complex chemistry while remaining far below the nuclear binding energies that power stars or the particle creation energies that require sophisticated accelerators. Human timescales span from fractions of seconds for neural responses to roughly 100 years for an entire lifetime. This temporal range enables us to observe many natural phenomena while missing others that occur too quickly or too slowly for direct perception. We can watch waves crash against shores but cannot directly observe continental drift or stellar evolution. Your mass of approximately 70 kilograms places you precisely between the atomic scale and planetary scale. You contain enough atoms, roughly 7 times 10 to the 27th, to exhibit classical rather than quantum behavior. Yet you remain small enough that gravitational effects stay negligible in your daily experience. This intermediate position explains why humans initially struggled to understand both quantum mechanics and general relativity. Our evolved intuition, perfectly adapted for survival at human scale, misleads us when extended to scales where different physical principles dominate natural phenomena. The tools and technologies we create extend our observational capabilities far beyond natural human limits. Microscopes reveal cellular and molecular structures. Telescopes bring distant galaxies within observational range. Particle accelerators probe subatomic realms. These instruments transform invisible phenomena into information our human-scale brains can process and understand. Yet, even our most sophisticated instruments ultimately interface with human observers. The data from the Hubble Space Telescope must be converted into visible images that human eyes can interpret. Particle collision data becomes visual displays that human pattern recognition can analyze. We remain fundamentally anchored to human scale, even when studying the largest and smallest phenomena in the universe. Human scale also defines our engineering capabilities. The strongest materials we can create using chemical bonds limit the size of structures we can build. The tallest buildings measure hundreds of meters rather than kilometers because molecular forces cannot support greater heights under Earth's gravitational field. Similarly, the smallest devices we can manufacture are limited by the wavelengths of light we use for lithography and the thermal motion of atoms at room temperature. Our technology extends our reach into other scales, but remains fundamentally constrained by human-scale physics and economics. The emergence of human intelligence at this particular scale may not be coincidental. Complex information processing requires systems large enough to contain billions of interconnected components, yet small enough for rapid signal transmission. Brains much larger than human size would suffer from signal delays across their volume, while smaller brains couldn't achieve sufficient complexity. This suggests that intelligence naturally emerges at scales roughly comparable to human dimensions, large enough for complexity, small enough for integration. Other intelligent species, if they exist, likely operate at similar physical scales regardless of their evolutionary origin. Human scale provides the foundation for measurement systems that make cosmic scales comprehensible. We define units like meters, kilograms, and seconds that relate to human experience, then extend these units through scientific notation to describe phenomena spanning dozens of orders of magnitude. Understanding our position at human scale prepares us for the journey ahead. Every dimension we explore, from mountains to galaxies, will be measured against this familiar reference point. Your 1.7-meter height becomes the ruler against which we'll measure the entire observable universe. The relationship between human scale and cosmic scale reveals something profound about the nature of scientific discovery. We exist at precisely the right scale to discover both the microscopic quantum world and the macroscopic cosmos. This remarkable coincidence enables our species to understand the universe across nearly 60 orders of magnitude in size. From this foundation of human scale, we now turn our attention to the largest features of our immediate environment, the mountains, oceans, and continents that define Earth's surface. These geological structures represent our first step into scales that begin to dwarf human experience while remaining within the familiar bounds of our home planet. Mount Everest rises 8.848 kilometers above sea level, piercing Earth's atmosphere like a stone monument to geological forces operating across millions of years. This peak represents the ultimate achievement of our planet's mountain-building processes, yet when measured against Earth's full diameter of 12,742 kilometers, it comprises merely 0.14% of our world's dimensions. To comprehend this relationship, imagine Earth as a perfectly smooth basketball measuring 24 centimeters in diameter. At this scale, Mount Everest would appear as a bump rising just 0.3 millimeters above the surface, barely detectable by running your finger across the ball's surface. The grandest mountain on Earth becomes nearly invisible when viewed against the planet's true proportions. This comparison reveals something fundamental about planetary architecture. The solid surface features that dominate human experience, towering peaks, deep valleys, vast plains, represent minor irregularities on what is essentially a smooth spherical object. Earth's surface varies by less than 20 kilometers from its deepest ocean trenches to its highest peaks, while the planet itself spans over 12,700 kilometers. The Mariana Trench, plunging 11.034 kilometers below sea level in the western Pacific Ocean, marks Earth's deepest accessible point. This underwater canyon could completely engulf Mount Everest with over 2 kilometers to spare, yet it too represents only 0.17% of Earth's diameter. Together, the highest peak and deepest trench span less than 20 kilometers, a variation that amounts to rounding error when calculating planetary dimensions. These extreme elevations result from tectonic processes that operate on timescales far exceeding human experience. The Himalayas continue rising as the Indian subcontinent drives northward into the Eurasian plate at roughly 5 centimeters per year. Over the past 50 million years, this collision has elevated rock formations that once lay beneath ancient oceans to heights where atmospheric pressure drops below 1/3 of sea level values. Mountain formation demonstrates how apparently solid Earth actually behaves as a fluid when viewed across geological timescales. Rock layers fold, compress, and thrust upward like slow-motion waves frozen in stone. The limestone composing Everest's summit contains marine fossils that lived in tropical seas before tectonic forces elevated them to altitudes where temperatures remain below freezing throughout the year. Continental dimensions reveal the true scale of Earth's surface features. The largest continent, Asia, spans roughly 8,800 kilometers from east to west and 9,600 kilometers from north to south. These distances approach significant fractions of Earth's circumference, demonstrating how continental landmasses represent major structural features rather than minor surface irregularities. The Pacific Ocean covers approximately 165 million square kilometers, encompassing nearly one-third of Earth's total surface area. This single ocean could contain all continental landmasses with substantial room remaining. Its maximum width between Asia and the Americas approaches 20,000 kilometers, more than half of Earth's circumference. Ocean depths average 3.8 kilometers globally, with most seafloor lying between 3 and 6 kilometers below sea level. This means that the solid surface we consider normal represents unusual elevated regions, while most of Earth's surface lies hidden beneath kilometers of water. Humans naturally think of sea level as the baseline, but from a planetary perspective, continents are elevated anomalies rising above the norm. The relationship between continental and oceanic scales becomes clear when examining Earth's crustal structure. Continental crust averages 35 to 40 kilometers thick and consists primarily of granite and other relatively light rock types. Oceanic crust measures only 6 to 10 kilometers thick and consists of denser basaltic materials. This thickness difference explains why continents float higher on the underlying mantle, creating the elevation contrast between land and sea floor. Atmospheric scale adds another dimension to Earth's architecture. The troposphere, where weather occurs and where humans can survive without artificial life support, extends only about 12 kilometers above sea level. This layer contains roughly 80% of atmospheric mass, yet represents less than 0.1% of Earth's radius. The entire atmosphere that sustains life exists within a layer thinner than the distance from New York to Washington, D.C. Commercial aircraft cruise at altitudes around 11 kilometers, flying near the boundary between troposphere and stratosphere. At this altitude, passengers look down on Mount Everest while remaining well within Earth's gravitational influence. The entire atmosphere that enables life on Earth appears as a gossamer-thin envelope when viewed from space. These terrestrial scales prepare us for understanding planetary perspectives. When astronauts photograph Earth from the International Space Station orbiting 400 kilometers above the surface, they observe the complete atmospheric envelope, weather systems spanning thousands of kilometers, and continental features stretching across substantial fractions of the visible hemisphere. The curvature of Earth becomes apparent at relatively modest altitudes. Pilots flying at 15 kilometers can detect the planet's curved horizon, while passengers in high-altitude aircraft observe atmospheric layers and the darkness of space beginning to appear above. These observations mark the transition from surface-based to orbital perspectives. Earth's diameter of 12,742 kilometers establishes the fundamental scale for terrestrial phenomena. This measurement, first calculated accurately by ancient Greek mathematicians using shadows and geometry, represents the boundary of our immediate cosmic environment. Everything larger requires us to look beyond our home planet to the broader solar system. The mass of Earth, approximately 6 times 10 to the 24th kilograms, creates the gravitational field that shapes our planet's structure and determines the behavior of everything from atmospheric circulation to ocean tides. This mass concentration in a sphere roughly 12,700 kilometers across generates surface gravity of 9.8 meters per second squared, the acceleration that defines our experience of weight and vertical orientation. Continental drift operates on scales that encompass entire ocean basins and affect global climate patterns. Over the past 200 million years, continents have migrated thousands of kilometers as tectonic plates carry them across Earth's surface at rates measured in centimeters per year. These motions demonstrate how planetary surfaces remain dynamic across geological time despite appearing static during human lifetimes. The relationship between human scale and continental scale reveals the first major conceptual leap in our journey outward. While humans can traverse continents through travel lasting hours to days, the geological processes that create and modify these features operate over millions to billions of years. This temporal scaling teaches us that increasing spatial scales often correspond to proportionally longer timescales. Understanding Earth's surface architecture provides essential context for appreciating our planet's position in the solar system. The features that seem enormous from human perspective, mountain ranges, ocean basins, entire continents, represent minor surface variations on a rocky sphere that itself becomes a mere speck when viewed against the scale of planetary orbits. Earth's 510 million square kilometers of total surface area could be completely covered by a circular region roughly 25,000 kilometers in diameter. This dimension approximates Earth's circumference, illustrating how our planet's entire surface area relates directly to its fundamental size. Every location you could ever visit, every landscape you could ever see, exists within this finite spherical boundary. The transition from terrestrial to orbital perspectives marks a crucial shift in understanding cosmic scale. Surface features that dominate human geography, rivers, mountain ranges, political boundaries, fade into invisibility when viewed from sufficient distance. This perspective shift prepares us for the even more dramatic transitions we'll encounter as we venture beyond Earth into the realm of planetary and stellar scales. From the heights of Everest and the depths of ocean trenches, we now lift our perspective beyond Earth's atmosphere to examine our planet's relationship with its nearest cosmic companion. The Earth-Moon system represents our first step into astronomical scales, where distances are measured in hundreds of thousands of kilometers rather than thousands. The Moon orbits Earth at an average distance of 384,400 kilometers, a measurement that represents humanity's first encounter with truly astronomical scales. To comprehend this distance, consider that you could fit 30 Earth-sized spheres in the space between our planet and its satellite, with room remaining for additional smaller worlds. This relationship transforms our understanding of what constitutes nearby in cosmic terms. The Moon appears large in our sky, subtending roughly the same angular diameter as the Sun, despite being 400 times closer. This cosmic coincidence enables total solar eclipses, a phenomenon that demonstrates the precision of orbital mechanics while providing one of nature's most spectacular displays. The Moon itself measures 3,474 kilometers in diameter, making it roughly 1/4 the size of Earth. This proportion is unusual among planetary satellites in our solar system. Most moons are much smaller relative to their parent planets, making the Earth-Moon system more like a double planet than a traditional planet-satellite arrangement. The formation of this system likely resulted from a catastrophic collision between early Earth and a Mars-sized object called Theia, approximately 4.5 billion years ago. This impact ejected material that eventually coalesced into the Moon, explaining the similar composition of Earth and lunar rocks, while accounting for the system's unusually large satellite-to-planet ratio. Lunar gravity, roughly 1/6 of Earth's surface gravity, creates tidal forces that fundamentally shape our planet's behavior. Ocean tides rise and fall twice daily as Earth rotates through the gravitational field created by the Moon's orbital motion. These tidal forces also gradually slow Earth's rotation while causing the Moon to spiral slowly outward, a process that will continue for billions of years. The Moon's influence extends far beyond ocean tides. tidal friction in Earth's crust dissipates energy that gradually lengthens our planet's day while increasing the lunar orbital period. Early in Earth's history, when the Moon orbited much closer, days lasted only about 10 hours while the Moon appeared dramatically larger in the sky. Measuring the Earth-Moon distance requires sophisticated techniques that demonstrate the precision of modern astronomy. Laser ranging experiments bounce light pulses off retroreflectors placed on the lunar surface by Apollo astronauts, measuring the round-trip travel time to determine distances accurate to within centimeters. These measurements reveal that the Moon recedes from Earth by approximately 3.8 centimeters per year. The 29.5-day lunar orbit period creates the monthly cycle that has influenced human culture throughout history. This period results from the complex interaction between the Moon's orbital motion around Earth and Earth's orbital motion around the Sun. The familiar phases, new moon, first quarter, full moon, third quarter, occur as we observe different portions of the lunar hemisphere illuminated by sunlight. Lunar exploration during the Apollo program provided humanity's first direct experience with traveling astronomical distances. The journey from Earth to Moon required approximately 3 days, with spacecraft reaching velocities around 11 kilometers per second to escape Earth's gravitational influence. These missions demonstrated the technological capabilities required for interplanetary travel while establishing human presence beyond Earth's atmosphere. The Moon's lack of atmosphere and magnetic field creates surface conditions unlike anything experienced on Earth. Daytime temperatures reach 127 degrees Celsius, while nighttime temperatures drop to negative 173 degrees Celsius. This extreme thermal variation results from the Moon's 28-day rotation period, which exposes each location to 2 weeks of direct sunlight followed by 2 weeks of darkness. Lunar surface features tell the story of early solar system history preserved in airless conditions. Impact craters ranging from microscopic pits to basins hundreds of kilometers across record the bombardment history that shaped all terrestrial planets. The largest lunar impact basin, the South Pole Aitken Basin, spans roughly 2,500 kilometers and penetrates deep into the lunar interior. The gravitational relationship between Earth and Moon creates phenomena visible to naked eye observers. Lunar libration, a slight rocking motion caused by orbital dynamics, allows Earth-based observers to see approximately 59% of the lunar surface over time. This motion results from the elliptical lunar orbit and the tilted lunar rotation axis. Understanding the Earth-Moon system requires thinking in 3 dimensions about orbital mechanics. The Moon's orbit is tilted roughly 5 degrees relative to Earth's orbital plane around the Sun, which explains why eclipses don't occur monthly. Solar and lunar eclipses happen only when the 3 bodies align along the line of orbital intersection, creating relatively rare astronomical events. The Moon's synchronous rotation, showing the same face to Earth throughout its orbit, demonstrates how tidal forces shape celestial mechanics. This phenomenon, called tidal locking, occurs because Earth's gravity created a permanent bulge in the Moon that acts like a gravitational handle, preventing the Moon from rotating independently relative to its orbital motion. Modern space missions reveal the Moon as a complex world with its own geological history. Lunar Maria, dark regions visible from Earth, consist of ancient lava flows that filled impact basins billions of years ago. Highland regions represent the Moon's original crustal material, heavily cratered and chemically distinct from the volcanic Maria. The Earth-Moon system serves as a natural laboratory for understanding gravitational physics. The precise measurements of lunar motion, enabled by laser ranging, provide tests of general relativity and constrain theories about the nature of gravity. These experiments detect relativistic effects that cause tiny deviations from classical orbital predictions. Water ice discovered in permanently shadowed lunar polar craters represents a resource that could support future human exploration. These deposits, likely delivered by comet impacts over billions of years, remain frozen in regions where temperatures never rise above -230 degrees Celsius. The Moon's geological inactivity preserves a record of conditions during the solar system's first billion years, information largely erased on Earth by plate tectonics and atmospheric weathering. Lunar samples returned by Apollo missions continue providing insights into early solar system processes, including the timing and intensity of the late heavy bombardment that affected all inner planets. Comparing Earth and Moon illuminates how planetary characteristics depend on mass, distance from the Sun, and other factors. Earth's larger mass retains a substantial atmosphere and generates internal heat through radioactive decay, enabling geological activity and liquid water. The Moon's smaller mass allowed its atmosphere to escape to space and its interior to cool quickly, creating a geologically dead world. The Earth-Moon distance of 384,400 kilometers establishes our first benchmark for astronomical measurements. This distance equals roughly 60 Earth radii, providing a convenient unit for measuring distances within planetary systems. The lunar orbit fits comfortably within the magnetosphere of larger planets like Jupiter, illustrating how the Earth-Moon system would be considered a close binary in other planetary contexts. Looking ahead to planetary scales, the Earth-Moon system occupies a tiny region within the vast space of our solar system. The distance to our nearest planetary neighbor, Venus, varies between 25 million and 260 million kilometers depending on orbital positions, roughly 65 to 675 times the Earth-Moon distance. This comparison reveals how the familiar scale of the Earth-Moon system becomes minuscule when extended to interplanetary dimensions. The gravitational sphere of influence around Earth, called the Hill sphere, extends roughly 1.5 million kilometers in the direction of the Sun. This region defines the boundary within which Earth's gravity dominates over solar gravitational effects. The Moon orbits well within this sphere, but the boundary itself extends nearly 4 times farther than the lunar orbit, illustrating the scale of gravitational influence around planetary bodies. From our cosmic dance with the Moon, we now expand our perspective to encompass the full solar system, a realm where distances are measured in millions rather than hundreds of thousands of kilometers, where planets dwarf our Earth-Moon system, and where the Sun's influence extends far beyond the orbit of the most distant planets. The solar system spans a region roughly 100,000 times wider than the Earth-Moon distance we just explored. To traverse from the Sun to the outer boundary of its gravitational influence requires traveling approximately 100,000 astronomical units, a distance so vast that light itself requires nearly 2 years to complete the journey. 1 astronomical unit, abbreviated as AU, equals the average Earth-Sun distance of roughly 150 million kilometers. This fundamental measurement provides our standard ruler for planetary distances, just as the meter serves for terrestrial measurements. Light travels this distance in approximately 8 minutes and 20 seconds, meaning we always see the Sun as it appeared over 8 minutes in the past. The inner solar system contains 4 terrestrial planets with dramatically different characteristics, despite their relatively similar distances from the Sun. Mercury, the innermost planet, orbits at 0.39 AU while maintaining a diameter of 4,880 kilometers, roughly 38% of Earth's diameter. This small world experiences surface temperatures ranging from 430 degrees Celsius on its sun-facing side to negative 170 degrees Celsius in permanent shadow. Venus orbits at 0.72 AU and measures 12,104 kilometers in diameter, approximately 95% of Earth's size. Despite receiving only twice Earth's solar radiation, Venus maintains surface temperatures around 464 degrees Celsius due to a runaway greenhouse effect caused by its dense carbon dioxide atmosphere. This demonstrates how atmospheric composition can dominate orbital distance in determining planetary conditions. Mars, orbiting at 1.52 AU, spans 6,779 kilometers in diameter, roughly 53% of Earth's size. This planet shows evidence of past liquid water flow despite currently maintaining surface conditions too cold and atmospheric pressure too low for liquid water stability. The contrast between past and present Martian conditions illustrates how planetary environments can evolve dramatically over geological timescales. The asteroid belt, extending roughly from 2.2 to 3.3 AU, contains millions of rocky objects ranging from dust particles to Ceres, which measures 946 kilometers in diameter. The total mass of all asteroid belt objects equals roughly 4% of the Moon's mass, demonstrating how the solar system's solid material concentrated primarily into the major planets during formation. Beyond Mars lies a dramatic transition to the realm of giant planets, where distances and sizes increase by orders of magnitude. Jupiter orbits at 5.2 AU, more than 5 times Earth's distance from the Sun, while maintaining a diameter of 139,820 kilometers. This makes Jupiter roughly 11 times wider than Earth, with a volume capable of containing approximately 1,300 Earth-sized planets. Jupiter's mass of 318 Earth masses equals more than twice the combined mass of all other planets. This gravitational dominance profoundly influences solar system architecture, deflecting comets, clearing orbital resonances, and likely preventing the formation of additional planets in the outer solar system. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, create a miniature solar system with dynamics comparable to the relationships between inner planets. Saturn, orbiting at 9.5 AU, measures 119,300 kilometers in diameter, while maintaining an average density lower than water. Its spectacular ring system extends from 7,000 to 80,000 kilometers above the planet's equator, yet maintains a thickness of typically less than 1 kilometer. These rings consist of countless ice and rock particles ranging from microscopic dust to house-sized boulders, all orbiting Saturn in accordance with Kepler's laws. The ring system demonstrates gravitational physics operating on vast scales with extraordinary precision. Shepherd moons maintain ring gaps through gravitational resonances, while density waves propagate through ring material like ripples in a cosmic pond. Ring particles closer to Saturn orbit faster than those farther out, creating the differential motion that prevents ring material from coalescing into larger bodies. Uranus, at 19.2 AU, and Neptune, at 30.1 AU, represent ice giants with diameters around 25,000 kilometers, roughly 4 times Earth's diameter. Both planets contain substantial amounts of water, methane, and ammonia ices surrounding rocky cores. Uranus rotates on its side, likely due to a collision during planetary formation, while Neptune exhibits the strongest winds in the solar system, despite receiving minimal solar heating. The discovery of Neptune through mathematical prediction, rather than direct observation, demonstrated the power of gravitational theory. Perturbations in Uranus's orbit led astronomers to calculate Neptune's position before telescopic confirmation, validating Newton's law of universal gravitation on solar system scales. Pluto, orbiting in the Kuiper belt between 30 and 49 AU, represents the most well-known member of a population of small, icy bodies in the outer solar system. With a diameter of 2,376 kilometers, Pluto is smaller than Earth's moon, yet maintains 5 known satellites, including Charon, which is roughly half Pluto's size. This system demonstrates how complex orbital dynamics can exist even among the smallest planetary bodies. The Kuiper belt extends from Neptune's orbit to roughly 50 AU and contains thousands of objects larger than 100 kilometers in diameter. These bodies preserve material from solar system formation 4.6 billion years ago, providing insights into conditions in the early solar nebula. Short-period comets originate primarily from this region when gravitational perturbations deflect objects into the inner solar system. Beyond the Kuiper belt lies the Oort cloud, a spherical shell of comets extending from roughly 2,000 to 100,000 AU from the Sun. This region contains trillions of icy objects with a total mass estimated at several Earth masses. Long-period comets originate from the Oort cloud when passing stars or galactic tidal forces disturb these distant objects, sending them on highly elongated orbits that bring them close to the Sun. The heliopause, marking the boundary where solar wind meets interstellar medium, lies roughly 120 AU from the Sun. Beyond this boundary, the Sun's direct influence diminishes while interstellar conditions begin to dominate. The Voyager 1 spacecraft crossed this boundary in 2012, becoming humanity's first artificial object to enter interstellar space while still remaining within the Sun's gravitational sphere of influence. Solar system formation occurred through gravitational collapse of a rotating molecular cloud approximately 4.6 billion years ago. The central condensation became the Sun, while surrounding material formed a protoplanetary disk from which planets accreted. This process explains the orderly arrangement of planetary orbits and the compositional differences between inner rocky planets and outer gas giants. The frost line, located roughly 2.7 AU from the Sun, marked the boundary where water could condense as ice during planetary formation. Interior to this line, rocky materials dominated planetary composition, while beyond it, abundant ice enabled the formation of massive planetary cores capable of accreting substantial atmospheric envelopes. Planetary migration likely occurred during the early solar system epoch, with Jupiter moving inward before reversing direction due to interactions with Saturn. This grand TAC model explains the asteroid belt's low mass, Mars's small size, and the overall architecture of the inner solar system. Such migration processes appear common in other planetary systems discovered around nearby stars. The solar system contains over 200 known moons, ranging from tiny, irregular asteroids captured into planetary orbits to large spherical bodies with complex geological histories. Europa, Enceladus and Titan maintain subsurface oceans that potentially harbor microbial life, while Io displays active volcanism driven by tidal heating from Jupiter's powerful gravitational field. Measuring solar system distances required centuries of increasingly sophisticated techniques. Early astronomers used parallax measurements of Mars during close approaches to establish the scale of interplanetary orbits. Radar ranging to Venus and spacecraft tracking now provide distance measurements accurate to within meters across the entire solar system. The solar system's age of 4.6 billion years comes from radiometric dating of meteorites, particularly calcium-aluminum-rich inclusions that represent the oldest solid materials formed in the solar nebula. This age approximately equals 1/3 of the universe's total age, indicating that our solar system, formed after several generations of stellar nucleosynthesis, had enriched the interstellar medium with heavy elements. Comparing our solar system to others discovered around nearby stars reveals both typical and unusual characteristics. Hot Jupiters, giant planets orbiting very close to their stars, appear common, while systems like ours, with giant planets in outer orbits and small rocky planets closer in, seem relatively rare. This suggests that planetary system architectures depend sensitively on formation conditions and evolutionary history. The scale of our planetary neighborhood spans 5 orders of magnitude from Mercury's orbit to the heliopause, yet this entire region appears as a point when viewed from the nearest stars. The next phase of our journey ventures beyond solar system boundaries into the realm of stellar distances, where measurements shift from astronomical units to light years and the Sun itself becomes just another star among billions. The Sun contains 99.86% of our solar system's total mass, while measuring 1,391,000 kilometers in diameter, approximately 109 times wider than Earth. To comprehend this scale, imagine Earth as a peppercorn measuring 1 millimeter across. At this scale, the Sun would appear as a sphere roughly 11 centimeters in diameter, while the nearest star would lie approximately 4,000 kilometers away. This stellar colossus generates energy through nuclear fusion reactions occurring in its core, where temperatures reach 15 million degrees Celsius and pressures exceed 250 billion times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei overcome electromagnetic repulsion and fuse into helium, converting approximately 4 million tons of matter into pure energy every second, according to Einstein's equation E equals mc squared. The energy production rate of 3.8 times 10 to the 26th watts exceeds human comprehension through direct comparison. This output equals roughly 100 billion times the total energy consumption of human civilization. Every square meter of the Sun's surface radiates 63 million watts, enough energy to power approximately 600,000 typical homes continuously. Nuclear fusion reactions in the solar core create photons that begin a remarkable journey toward the surface. These high-energy gamma rays scatter countless times through the dense solar interior, gradually losing energy as they transform into visible light photons. This random walk process requires photons approximately 100,000 years to travel from the core to the surface, even though the same distance would require only 2.3 seconds for unimpeded light travel. The Sun's layered structure demonstrates how hydrostatic equilibrium balances gravitational collapse against radiation pressure across stellar dimensions. The core extends roughly 150,000 kilometers from the center, containing 50% of the Sun's mass within only 2% of its volume. The radiative zone extends to 500,000 kilometers radius, where energy transport occurs primarily through photon diffusion. The convective zone, extending from 500,000 kilometers radius to the visible surface, transports energy through massive circulation patterns. Hot plasma rises from the interior while cooler material descends, creating convection cells visible as granulation patterns on the solar surface. Individual granules measure roughly 1,000 kilometers across, comparable to the distance from New York to Jacksonville, Florida. Solar surface temperature averages 5,778 degrees Celsius, producing the characteristic yellow-white light that illuminates our planet. This temperature determines the Sun's spectral characteristics and explains why peak solar radiation occurs in the visible portion of the electromagnetic spectrum, a cosmic coincidence that enabled the evolution of photosynthesis and complex vision systems on Earth. The solar atmosphere extends far beyond the visible surface through increasingly hot and tenuous layers. The chromosphere, visible during solar eclipses as a reddish glow, reaches temperatures around 20,000 degrees Celsius, despite its greater distance from the fusion core. This temperature inversion reflects complex magnetic heating processes that remain incompletely understood. The solar corona, extending millions of kilometers from the surface, maintains temperatures exceeding 1 million degrees Celsius through mechanisms related to magnetic field reconnection and wave heating. Coronal gas continuously escapes as solar wind, a stream of charged particles flowing outward at speeds between 300 and 800 kilometers per second throughout the solar system. This solar wind creates the heliosphere, a bubble of charged particles extending well beyond Pluto's orbit. The heliopause, where solar wind pressure balances interstellar medium pressure, lies roughly 120 astronomical units from the Sun. Within this vast region, solar magnetic fields and particle flows dominate conditions despite the enormous distances involved. The Sun's magnetic field, generated by differential rotation and convection in its interior, creates an 11-year activity cycle. During solar maximum, increased magnetic activity produces more sunspots, solar flares, and coronal mass ejections. These events demonstrate the Sun's dynamic nature and its ability to affect planetary environments across astronomical distances. Solar flares release energy equivalent to billions of nuclear weapons in minutes, accelerating particles to near light speed and producing electromagnetic radiation across the entire spectrum. The most powerful flares can disrupt satellite communications, damage electronic systems, and create auroras visible at unusually low latitudes on Earth. The Sun's gravitational influence extends far beyond its visible surface through its effect on planetary orbits and the structure of the entire solar system. At Earth's orbital distance, solar gravity produces an acceleration of 0.006 meters per second squared toward the Sun, roughly 1,600 times weaker than Earth's surface gravity, but sufficient to maintain our planet's orbital motion. Stellar classification places the Sun as a G2V dwarf star, indicating its surface temperature, spectral characteristics, and main sequence status. This classification reveals that the Sun represents a fairly typical star among the roughly 100 billion stars in our galaxy. Approximately 75% of stars are smaller and cooler than the Sun, while 25% are larger and hotter. The Sun's main sequence lifetime of approximately 10 billion years is roughly half complete. As nuclear fuel in the core gradually depletes, the Sun will slowly increase in luminosity while maintaining relatively stable surface conditions for another 5 billion years. This extended stability enabled the development of complex life on Earth and suggests similar opportunities may exist around comparable stars throughout the galaxy. Comparing the Sun to other stellar types reveals the remarkable diversity of stellar properties. Red dwarf stars, comprising roughly 75% of all stars, measure between 0.1 and 0.5 solar masses while maintaining surface temperatures around 3,000 to 4,000 degrees Celsius. These stars burn hydrogen so slowly that they can remain stable for hundreds of billions of years, far longer than the current age of the universe. White dwarf stars represent stellar remnants with masses comparable to the Sun, compressed into volumes similar to Earth. These objects maintain surface temperatures around 50,000 degrees Celsius immediately after formation, but gradually cool over billions of years. White dwarfs demonstrate how gravity can compress matter to densities exceeding 1 ton per cubic centimeter. At the opposite extreme, supergiants like Betelgeuse and Rigel exceed the Sun's mass by factors of 10 to 40, while expanding to sizes that would engulf the inner planets if placed in our solar system. These massive stars consume nuclear fuel rapidly, maintaining lifetimes measured in millions rather than billions of years before exploding as supernova. Neutron stars formed during supernova explosions compress stellar core material to nuclear density, roughly 100 million tons per cubic centimeter. These objects measure approximately 20 kilometers in diameter, while containing more mass than the Sun, creating surface gravity 100 billion times stronger than Earth's. A sugar cube of neutron star material would weigh roughly as much as Mount Everest. Black holes represent the ultimate expression of gravitational collapse, creating regions where space-time curvature becomes so extreme that not even light can escape. Stellar mass black holes form from stars exceeding roughly 25 solar masses, while supermassive black holes found in galaxy centers contain millions to billions of solar masses through mechanisms that remain incompletely understood. The Sun's position within the galaxy places it approximately 26,000 light-years from the galactic center in a region called the Orion Arm or local arm. This location provides relatively stable conditions with moderate stellar density and low supernova frequency compared to regions closer to the galactic center or in spiral arms with active star formation. Solar oscillations reveal the Sun's internal structure through helioseismology, the study of acoustic waves propagating through stellar interiors. These pressure waves, created by turbulent convection, travel at different speeds through regions of varying density and composition, enabling astronomers to map solar interior conditions with extraordinary precision. The solar neutrino flux reaching Earth provides direct evidence of nuclear fusion reactions occurring in the solar core. These nearly massless particles interact so weakly with matter that they travel directly from the core to Earth in approximately 8 minutes, carrying information about current fusion rates. Detecting these elusive particles required building massive underground detectors and solving the solar neutrino problem that puzzled physicists for decades. Understanding stellar evolution reveals that the Sun formed from a collapsing molecular cloud approximately 4.6 billion years ago through gravitational instability. As the proto-Sun contracted, gravitational potential energy converted to thermal energy until core temperatures reached the threshold for hydrogen fusion. This process demonstrates how gravity serves as the fundamental driver of stellar formation and evolution throughout the universe. The Sun's chemical composition, roughly 73% hydrogen and 25% helium by mass, reflects conditions in the early universe, plus contributions from previous generations of stars that synthesized heavier elements through nuclear processes. Elements heavier than lithium comprise only 2% of the Sun's mass, yet these trace constituents enable the complex chemistry required for planetary formation and biological evolution. From our exploration of stellar scales, we now venture beyond the Sun to examine the vast distances separating our star from its nearest neighbors. The journey from planetary to interstellar scales represents one of the most dramatic transitions in our cosmic voyage, where distances increase by factors of millions and light itself becomes our primary measuring tool. The nearest star to our Sun lies 4.24 light-years away, a distance so vast that the fastest spacecraft ever built by humans would require over 70,000 years to complete the journey. This star, Proxima Centauri, appears as an unremarkable red dot even through powerful telescopes, yet it represents our closest stellar neighbor in a galaxy containing hundreds of billions of similar objects. 1 light-year equals approximately 9.46 trillion kilometers, or 63,240 astronomical units. To comprehend this distance, consider that light travelling from Proxima Centauri began its journey over 4 years ago, before the most recent presidential election, before the COVID-19 pandemic began, before countless events that seem recent in human experience. When we observe Proxima Centauri, we literally see it as it existed in our past. The Alpha Centauri system, containing Proxima Centauri along with the brighter stars Alpha Centauri A and B, demonstrates how stellar systems can differ dramatically from our single-star arrangement. Alpha Centauri A and B orbit each other every 80 years at distances ranging from 11 to 35 AU, comparable to the orbital distances of Saturn and Pluto in our solar system. Proxima Centauri orbits this pair at roughly 15,000 AU, taking approximately 500,000 years to complete one revolution. Alpha Centauri A closely resembles our Sun with a mass of 1.1 solar masses and surface temperature around 5,800 degrees Celsius. Alpha Centauri B appears slightly smaller and cooler, with 0.9 solar masses and surface temperature around 5,300 degrees Celsius. This binary system likely formed from the same molecular cloud 4.4 billion years ago, demonstrating how stellar birth often occurs in groups rather than isolation. Proxima Centauri, despite being our nearest stellar neighbour, represents a typical red dwarf star with only 0.12 solar masses and surface temperature around 3,000 degrees Celsius. Red dwarf stars comprise roughly 75% of all stars in our galaxy, making Proxima Centauri more representative of typical stellar properties than our Sun's intermediate characteristics. The discovery of potentially habitable planets around nearby stars revolutionizes our understanding of cosmic real estate. Proxima Centauri B, orbiting at 0.05 AU from its host star, receives stellar radiation similar to Earth despite its close orbital distance, because red dwarf stars produce much less energy than the Sun. This planet completes one orbit every 11.2 days, while potentially maintaining surface conditions suitable for liquid water. Stellar parallax measurements enable precise distance determinations to nearby stars through geometric principles discovered by ancient mathematicians. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. The parallax angle for Proxima Centauri measures 0.768 arcseconds, an angular measurement so small that it equals the width of a dime viewed from 4 kilometers away. Barnard's star, lying 5.96 light-years away, demonstrates how stellar motion across the sky can be detected over human timescales. This red dwarf star exhibits the largest proper motion of any known star, moving 10.3 arcseconds per year relative to background stars. At this rate, Barnard's star would cross the apparent diameter of the Moon in roughly 180 years, fast motion by astronomical standards, yet barely perceptible during individual human lifetimes. Wolf 359, located 7.86 light-years from Earth, represents one of the least luminous stars known. This red dwarf produces only 0.001% of the Sun's energy output, despite maintaining nuclear fusion reactions in its core. Such dim stars remain invisible to naked eye observation despite their relatively close distances, illustrating how stellar luminosity varies dramatically among different stellar types. Sirius, the brightest star visible in Earth's night sky, lies 8.66 light-years away, while producing roughly 25 times the Sun's luminosity. This binary system contains Sirius A, a main-sequence star with 2.0 solar masses, orbited by Sirius B, a white dwarf companion with 1.0 solar masses, compressed into a volume roughly the size of Earth. The orbital period of 50 years creates observable changes in the system's gravitational effects and spectroscopic properties. The white dwarf Sirius B demonstrates stellar evolution's ultimate fate for Sun-like stars. This dense stellar remnant maintains surface temperatures around 25,000 degrees Celsius while slowly cooling over billions of years. Its gravitational field at the surface exceeds Earth's surface gravity by roughly 400,000 times, creating extreme space-time curvature that affects light propagation and atomic behavior. Procyon, located 11.46 light-years away, represents another binary system containing a main sequence star and white dwarf companion. Procyon A appears slightly larger and more luminous than the Sun, while Procyon B completed its evolution to white dwarf status relatively recently, within the past 1.2 billion years. This system demonstrates how binary star evolution can proceed at different rates depending on initial stellar masses. Stellar spectroscopy reveals the chemical composition, temperature and physical conditions of stars across interstellar distances. Spectral lines, produced by elements in stellar atmospheres, create unique fingerprints that identify specific atoms and their excitation states. These techniques enable astronomers to determine that nearby stars generally contain similar heavy element abundances to the Sun, indicating comparable formation environments and evolutionary histories. Stellar classification systems organize the diversity of stellar types according to surface temperature, luminosity, and spectral characteristics. The Morgan-Keenan system uses letters O, B, A, F, G, K, M to denote decreasing surface temperatures, with additional luminosity classes distinguishing between main sequence stars, giants and supergiants. Our Sun's G2V classification indicates intermediate temperature and main sequence status. Red dwarf stars like Proxima Centauri maintain nuclear fusion through the proton-proton chain reaction, occurring at much lower rates than in Sun-like stars. Their fully convective interiors enable complete mixing of nuclear fuel throughout the stellar volume, allowing red dwarfs to maintain hydrogen fusion for hundreds of billions of years, far longer than the current age of the universe. The habitable zones around different stellar types vary dramatically based on stellar luminosity and spectral characteristics. Red dwarf habitable zones lie very close to the star, typically between 0.1 and 0.2 AU, while more luminous stars maintain habitable zones at several AU distances. These differences affect planetary atmospheric evolution and the likelihood of maintaining stable surface conditions over geological timescales. Stellar formation in our galactic neighborhood occurred through multiple episodes over billions of years, creating stellar populations with different ages and chemical compositions. The oldest nearby stars formed over 10 billion years ago, when the galaxy contained much lower abundances of elements heavier than hydrogen and helium. Younger stars like the Sun incorporated heavier elements synthesized by previous stellar generations through nuclear fusion and supernova explosions. Brown dwarf objects, with masses between roughly 0.01 and 0.08 solar masses, represent failed stars that never achieved sufficient core temperatures for sustained hydrogen fusion. These objects gradually cool and dim over time, while maintaining planetary rather than stellar characteristics. Several brown dwarfs exist within 20 light-years of Earth, including Luhmann 16 at 6.59 light-years distance. The search for exoplanets around nearby stars has revealed thousands of confirmed planetary systems with architectures often differing dramatically from our solar system. Hot Jupiters orbiting very close to their host stars, super-Earths with masses between Earth and Neptune, and compact multi-planet systems demonstrate that planetary system formation produces enormous diversity in outcomes. Transit photometry and radial velocity measurements enable detection and characterization of exoplanets across interstellar distances. When a planet passes in front of its host star, as viewed from Earth, it blocks a tiny fraction of stellar light proportional to the planet's cross-sectional area. Doppler shifts in stellar spectra reveal the gravitational influence of orbiting planets on their host star's motion. Atmospheric characterization of nearby exoplanets provides insights into planetary composition, climate, and potential habitability. Transmission spectroscopy during planetary transits reveals atmospheric constituents through their absorption signatures, while emission spectroscopy measures thermal radiation from planetary atmospheres. These techniques enable astronomers to study worlds orbiting other stars with increasing sophistication. The nearest stellar neighbors define our local galactic environment and provide natural laboratories for testing theories of stellar evolution, planetary formation, and astrobiology. Understanding these systems establishes the foundation for comprehending stellar populations on galactic scales, where billions of similar systems contribute to the structure and evolution of the Milky Way Galaxy. Interstellar distances dwarf all previous scales in our cosmic journey, yet they represent merely the smallest steps into galactic dimensions. The 4.24 light-year distance to Proxima Centauri equals roughly 1/10,000th of our galaxy's diameter, illustrating how individual stellar separations relate to the vast congregations of stars that comprise galactic structures. The transition from stellar to galactic scales introduces concepts of stellar demographics, chemical evolution, and large-scale structure that govern how billions of individual stars organize into coherent galactic systems. Our next chapter explores the Milky Way Galaxy, our home among hundreds of billions of stars arranged in spiral patterns spanning 100,000 light-years. The Milky Way Galaxy stretches approximately 100,000 light-years from edge to edge, while maintaining a thickness of roughly 1,000 light-years through its disk, proportions resembling a dinner plate, with our solar system located about 2/3 of the way from center to rim. This vast stellar city contains between 100 and 400 billion individual stars, each potentially hosting its own system of planets and moons. To comprehend galactic dimensions, consider that light requires 100,000 years to traverse the Milky Way's diameter. This means that astronomers observing the galaxy's far side literally see those regions as they existed 100,000 years ago, before modern humans had fully developed agriculture, writing, or complex civilizations. The galaxy we observe represents a composite image spanning tens of thousands of years of galactic history. Our solar system orbits the galactic center at a distance of approximately 26,000 light-years, maintaining an orbital velocity around 220 kilometers per second. At this speed, one complete galactic orbit requires roughly 225 million years, a period astronomers call a galactic year. Since Earth's formation 4.6 billion years ago, our planet has completed approximately 20 galactic orbits, while life evolved from single-celled organisms to technological civilization. The galactic center harbors a supermassive black hole called Sagittarius A, with periods as short as 16 years, providing direct tests of general relativity in the strongest gravitational fields accessible to astronomical observation. These stellar orbits exhibit relativistic precession, gravitational redshift, and other effects predicted by Einstein's theory, confirming our understanding of gravity in extreme environments. The Milky Way's spiral structure consists of four major arms: Perseus, Sagittarius, Centaurus, and Outer, that wrap around the galactic center with a pitch angle of roughly 12 degrees. Our solar system resides in a minor arm called the Orion Arm or Local Arm, positioned between the Perseus and Sagittarius arms. This location provides relatively stable conditions with moderate stellar density and infrequent supernova explosions. Spiral arms represent density waves propagating through the galactic disk, rather than fixed structures rotating as solid bodies. Stars and gas periodically enter and exit spiral arms during their galactic orbits, with enhanced star formation occurring as material compresses while passing through these density enhancements. This process creates the bright young stars that define spiral arm visibility, while older stars populate regions between arms. The galactic disk contains roughly 90% of the galaxy's visible stars, organized into distinct stellar populations with different ages and chemical compositions. Population 1 stars, including our Sun, formed relatively recently from gas enriched with heavy elements synthesized by previous stellar generations. Population 2 stars formed earlier when the galaxy contained fewer heavy elements, resulting in different spectral characteristics and spatial distributions. The galactic halo extends roughly 100,000 light-years from the galactic center as a roughly spherical distribution of old stars, globular clusters, and dark matter. Globular clusters within the halo contain some of the oldest stars in the galaxy. Objects formed within the first billion years after galactic assembly, roughly 13 billion years ago. Dark matter comprises roughly 85% of the Milky Way's total mass, while remaining invisible to electromagnetic radiation. This mysterious component reveals its presence through gravitational effects on stellar motions, galaxy rotation curves, and gravitational lensing of background objects. The dark matter halo likely extends several 100,000 light-years from the galactic center, far beyond the visible stellar components. Galactic rotation creates one of astronomy's most significant mysteries through the observation that stellar orbital velocities remain roughly constant at large distances from the galactic center. Newton's laws predict that rotation velocities should decrease with distance, similar to planetary motion in the solar system. The flat rotation curve observed in the Milky Way and other galaxies provides primary evidence for dark matter's existence. The interstellar medium filling space between stars consists of gas and dust, with an average density of roughly 1 atom per cubic centimeter, trillions of times more tenuous than the best vacuum achievable in terrestrial laboratories. Despite this extremely low density, the interstellar medium contains significant total mass and serves as the raw material for ongoing star formation throughout the galaxy. Molecular clouds within the interstellar medium provide the birth sites for new stars when gravitational collapse overcomes internal gas pressure. These regions, often called stellar nurseries, contain thousands of solar masses of material at temperatures around 10 to 20 degrees above absolute zero. The Orion Nebula, visible to naked-eye observers, represents the nearest major star-forming region at roughly 1,340 light-years distance. Star formation occurs through a complex process beginning when molecular clouds fragment into smaller cores that undergo gravitational collapse. As protostellar cores contract, they heat up and eventually reach temperatures sufficient for nuclear fusion. This process typically produces clusters of stars, rather than isolated objects, explaining why most stars form in groups before dispersing throughout the galactic disk over hundreds of millions of years. The Milky Way's star formation rate currently averages roughly 1 to 3 solar masses per year, indicating that our galaxy maintains active stellar production despite its advanced age of approximately 13 billion years. This ongoing star formation recycles material through stellar death processes, including planetary nebulae from low-mass stars and supernova explosions from high-mass stars. Supernova explosions play crucial roles in galactic evolution by synthesizing and distributing heavy elements throughout the interstellar medium, while driving turbulence and shock waves that can trigger additional star formation. Type 2 supernovae from massive stars produce elements like oxygen, silicon, and iron, while Type Ia supernovae from white dwarf explosions contribute different elemental abundances to galactic chemical evolution. The metallicity gradient observed across the galactic disk shows higher heavy element abundances near the galactic center, where star formation has been most active throughout galactic history. Our solar system's location exhibits intermediate metallicity that enabled the formation of terrestrial planets and complex chemistry necessary for biological evolution. Galactic cannibalism describes how the Milky Way has grown through mergers with smaller galaxies throughout its evolutionary history. Tidal streams of stars stripped from disrupted satellite galaxies remain visible as stellar streams crossing the galactic halo. The largest ongoing merger involves the Sagittarius dwarf elliptical galaxy, which is being gradually torn apart and incorporated into the Milky Way's structure. The galactic magnetic field, with typical strengths around 10 microgauss, influences charged particle motion and cosmic ray propagation throughout the galaxy. This magnetic field likely originates from a galactic dynamo process driven by differential rotation and convective motions within the galactic disk. Magnetic fields also affect star formation by providing support against gravitational collapse in molecular clouds. Cosmic rays, high-energy particles accelerated to relativistic speeds, permeate the galaxy and interact with magnetic fields, gas, and dust throughout the interstellar medium. These particles likely originate from supernova remnants, pulsar wind nebulae, and other high-energy astrophysical phenomena. Cosmic rays contribute to interstellar heating and ionization, while potentially affecting biological evolution through increased mutation rates. The Milky Way's satellite galaxy system includes over 50 known dwarf galaxies, with the Large and Small Magellanic Clouds being the most prominent members visible from Earth's southern hemisphere. These satellite galaxies orbit the Milky Way at distances ranging from roughly 25,000 to 1 million light-years, demonstrating how galactic gravitational influence extends far beyond the visible stellar disk. Recent surveys have discovered numerous ultra-faint dwarf galaxies orbiting the Milky Way, objects containing only thousands of stars, while maintaining dark matter masses comparable to much larger galaxies. These discoveries suggest that the Milky Way's halo may contain hundreds of satellite galaxies, most too faint for detection with current technology. The galactic coordinate system enables astronomers to specify locations within the Milky Way using galactic longitude and latitude referenced to the galactic center and galactic plane. This coordinate system proves essential for studying galactic structure, stellar motions, and the distribution of various galactic components across the sky. Stellar kinematics throughout the galaxy reveal complex motion patterns that provide insights into galactic formation and evolution. Thick disk stars exhibit larger vertical motions and velocity dispersions compared to thin disk stars, suggesting formation during more turbulent early epochs. Halo stars display highly eccentric orbits with random orientations, consistent with formation through galactic mergers. The zone of avoidance near the galactic plane prevents optical observations of external galaxies in roughly 20% of the sky due to dust extinction from the Milky Way's interstellar medium. This dust absorption demonstrates how our galaxy's own material affects astronomical observations, while highlighting the importance of multi-wavelength astronomy for complete sky coverage. Radio astronomy reveals galactic structure through 21-centimeter hydrogen emission, molecular line observations, and synchrotron radiation from cosmic ray electrons. These radio wavelengths penetrate interstellar dust that blocks optical light, enabling studies of galactic structure and dynamics throughout the entire galactic disk. The Milky Way's future evolution will be dramatically affected by its approaching collision with the Andromeda Galaxy in approximately 4.5 billion years. Computer simulations predict that this merger will create a large elliptical galaxy dubbed Milkomeda, while disrupting both galaxies' spiral structures. Our solar system will likely survive this merger, but may be relocated to a different region of the combined galaxy. From our position within the Milky Way, we observe only portions of galactic structure, while remaining embedded within the system we study. Understanding the complete three-dimensional architecture of our galaxy requires combining observations at multiple wavelengths with theoretical models of galactic formation and evolution. This challenge parallels attempting to map a vast city while standing at street level rather than viewing it from above. The Milky Way represents just one galaxy among billions throughout the observable universe, yet it provides our most detailed laboratory for understanding galactic physics, stellar evolution, and the conditions that enable planetary systems and biological evolution. Our galaxy's properties, size, mass, star formation rate, chemical composition, appear typical of large spiral galaxies, suggesting that similar conditions may exist throughout much of the universe. The transition from galactic to intergalactic scales represents another dramatic leap in cosmic perspective, where distances increase by factors of dozens, while revealing how galaxies themselves organize into larger structures. Our next exploration ventures beyond the Milky Way to examine our local group of galaxies and the cosmic web that connects all galactic systems across the observable universe. Beyond the Milky Way's 100,000 light-year expanse lies a gravitationally bound collection of over 80 galaxies spanning approximately 10 million light-years. This galactic congregation, known as the local group, represents our immediate cosmic neighborhood and provides the first glimpse of how galaxies organize themselves into larger structures throughout the universe. The local group's two dominant members, the Milky Way and Andromeda Galaxy, contain the vast majority of the group's total mass and luminosity. These spiral giants orbit their common center of mass, while dozens of smaller satellite galaxies follow complex orbital patterns within the group's gravitational influence. The relationship resembles a binary star system surrounded by planetary companions but operating on scales millions of times larger. The Andromeda Galaxy, also known as M31, spans roughly 220,000 light-years in diameter, more than twice the Milky Way's size, while containing approximately 1 trillion stars. Located 2.5 million light-years from Earth, Andromeda appears as a faint smudge to naked-eye observers despite being the most distant object visible without telescopic assistance. Light currently reaching us from Andromeda began its journey when early human ancestors first developed stone tool technologies. Andromeda's mass of roughly 1.5 trillion solar masses exceeds the Milky Way's estimated mass of 0.8 to 1.5 trillion solar masses, making it the local group's gravitational anchor. This massive galaxy approaches us at approximately 110 kilometers per second, indicating that despite the universe's overall expansion, local gravitational forces overcome cosmic expansion within galaxy groups and clusters. The approaching merger between Milky Way and Andromeda, predicted to occur in approximately 4.5 billion years, will fundamentally transform our cosmic neighborhood. Computer simulations suggest the galaxies will first interact through tidal forces before settling into elliptical orbits and eventually coalescing into a single large elliptical galaxy. This process will likely trigger intense star formation episodes while redistributing stellar populations throughout the merged system. The Triangulum Galaxy, M33, lying approximately 3 million light-years away, represents the local group's third largest member, with roughly 40 billion stars arranged in prominent spiral arms. This galaxy demonstrates that spiral structure can persist in environments with significant gravitational interactions, as Triangulum likely experiences tidal forces from both Andromeda and the Milky Way. Satellite galaxies throughout the local group illustrate how galactic hierarchies organize matter across cosmic scales. The large and small Magellanic Clouds orbiting the Milky Way at distances around 160,000 and 200,000 light-years respectively contain several billion stars each, while showing evidence of ongoing tidal disruption from their larger companion. The Magellanic Clouds demonstrate active star formation triggered by gravitational interactions with the Milky Way. The Large Magellanic Cloud hosts the Tarantula Nebula, one of the most active star-forming regions in the local group, where massive star clusters form from dense molecular clouds compressed by tidal forces and stellar winds. Dwarf elliptical galaxies comprise the majority of local group members, yet contribute relatively little to the total stellar mass. These systems, typically containing millions rather than billions of stars, appear to be dominated by dark matter, with stellar mass-to-light ratios far exceeding those of larger galaxies. Examples include the Sculptor Dwarf, Draco Dwarf, and numerous ultra-faint dwarfs discovered in recent surveys. The distribution of satellite galaxies around both the Milky Way and Andromeda exhibits unexpected patterns that challenge theoretical predictions. Satellite galaxies tend to align in thin planes rather than distributing randomly throughout the host galaxy's halo, suggesting that galaxy formation and evolution involve processes more complex than simple hierarchical assembly within dark matter halos. Ultra-faint dwarf galaxies represent the least luminous galaxies known, containing only hundreds to thousands of stars, while maintaining total masses dominated by dark matter. These systems provide crucial laboratories for understanding galaxy formation in the early universe and the nature of dark matter on small scales. Their survival as distinct entities suggests that dark matter halos can persist even when stellar formation proves extremely inefficient. The local group's total mass, approximately 2 to 5 trillion solar masses, remains distributed roughly 85% as dark matter and 15% as ordinary matter. This composition matches observations of larger cosmic structures while demonstrating that dark matter dominance extends across all scales, from individual galaxies to galaxy groups. Measuring distances within the local group requires sophisticated techniques extending beyond the parallax methods used for nearby stars. Cepheid variable stars, with their period luminosity relationship, provide standard candles for measuring distances to Andromeda and other local group members. More recently, tip-of-the-red giant branch stars and surface brightness fluctuations enable distance measurements with improved precision. The local group's motion relative to the cosmic microwave background reveals that our entire galactic collection moves at approximately 630 kilometers per second toward the constellation Hydra. This motion reflects gravitational influences from larger structures, including the Virgo cluster and more distant galaxy concentrations that shape local group dynamics despite their enormous distances. Tidal interactions throughout the local group create streams of stars and gas connecting member galaxies. The Magellanic Stream, extending over 100 degrees across the southern sky, consists of neutral hydrogen gas stripped from the Magellanic Clouds during their orbital motion around the Milky Way. Similar features around Andromeda indicate that tidal stripping represents a common process in galaxy group environments. The local group provides a natural laboratory for studying galaxy evolution under conditions of moderate gravitational interaction. Unlike galaxies in rich clusters that experience rapid encounters and harsh environments, local group members interact more gently over longer timescales, enabling detailed observations of tidal effects, star formation histories, and chemical evolution patterns. Chemical abundances throughout local group galaxies reflect different evolutionary histories and star formation efficiencies. Dwarf galaxies generally exhibit lower metallicities than larger spiral galaxies, consistent with less efficient retention of heavy elements produced by stellar nucleosynthesis. These abundance patterns provide constraints on theoretical models of galaxy formation and feedback processes. The intergalactic medium within the local group contains hot, ionized gas, detectable through X-ray emission and absorption lines toward background quasars. This material likely originates from galactic winds driven by stellar feedback processes, demonstrating how galaxies enrich their surrounding environments with metals and energy throughout cosmic history. Star formation histories, reconstructed from observations of resolved stellar populations, reveal that local group galaxies experience different evolutionary pathways. Some dwarf galaxies exhibit extended star formation over cosmic time, while others show evidence for truncated star formation histories possibly caused by environmental effects or internal feedback processes. The local group's isolation from rich galaxy clusters creates conditions enabling detailed studies of galaxy interactions without the complicating effects of high-velocity encounters and harsh intra-cluster environments. This isolation also means that local group galaxies have evolved primarily through internal processes and mutual interactions rather than external environmental influences. Local group astronomy drives technological developments in observational techniques, including adaptive optics systems that correct atmospheric turbulence, wide-field survey cameras that map large sky areas efficiently, and spectroscopic instruments capable of measuring radial velocities and chemical abundances for individual stars in external galaxies. The discovery of numerous ultra-faint local group members through surveys like the Sloan Digital Sky Survey demonstrates that galaxy groups likely contain far more low-mass galaxies than previously recognized. These discoveries suggest that the local group may ultimately contain hundreds of satellite galaxies, most too faint for detection with current technology. Understanding local group dynamics provides insights into the formation and evolution of galaxy groups throughout the universe. The local group's properties, total mass, galaxy number density, morphology distribution, appear typical of galaxy groups at similar redshifts, suggesting that our cosmic neighborhood represents a fair sample of how galaxies organize on intermediate scales. The transition from local group scales to larger cosmic structures introduces concepts of dark energy, cosmic expansion, and the large-scale distribution of matter throughout the universe. While gravitational binding maintains local group integrity against cosmic expansion, larger separations require understanding how expansion affects structure formation and evolution across cosmic time. Future local group evolution will be dominated by the Milky Way-Andromeda merger, while smaller satellite galaxies experience ongoing tidal disruption and possible accretion onto the central galaxies. These processes will gradually concentrate local group mass into fewer, more massive objects while creating extended tidal debris throughout the group's volume. The local group serves as humanity's extended cosmic home, encompassing all the galaxies with which we share gravitational binding and common evolutionary destiny. From this galactic neighborhood, we now venture into the realm of galaxy clusters and superclusters, where hundreds to thousands of galaxies congregate across scales spanning hundreds of millions of light-years. The Virgo cluster dominates our local cosmic landscape, containing over 1,300 member galaxies distributed across a region roughly 15 million light-years in diameter. Located approximately 54 million light-years from the local group, this massive galactic congregation demonstrates how gravity organizes hundreds of individual galaxies into coherent structures spanning scales that dwarf our previous explorations. Understanding galaxy clusters requires recognizing that these represent the largest gravitationally bound structures in the universe. While cosmic expansion drives most galaxies away from each other, galaxy clusters maintain their integrity through the combined gravitational influence of hundreds of member galaxies, plus vast quantities of dark matter and hot intracluster gas. The Virgo cluster's central region is dominated by M87, a giant elliptical galaxy containing several trillion stars and harboring a supermassive black hole with 6.5 billion solar masses. This black hole powers a relativistic jet extending over 5,000 light-years from the galactic core, a phenomenon captured in the first direct image of a black hole by the Event Horizon Telescope collaboration in 2019. Galaxy clusters contain three primary components: member galaxies comprising roughly 5% of total mass, hot intracluster gas accounting for 10 to 15%, and dark matter constituting 80 to 85%. This mass distribution demonstrates dark matter's dominance on the largest gravitationally bound scales, while revealing how ordinary matter organizes within dark matter scaffolding. The intracluster medium consists of ionized gas heated to temperatures between 10 and 100 million degrees Celsius through gravitational compression and shock heating during cluster formation. This extremely hot gas emits X-rays detectable by space-based telescopes, providing a direct probe of cluster mass distribution and evolutionary history. Gravitational lensing by galaxy clusters creates some of astronomy's most spectacular phenomena, while providing powerful tools for studying both cluster properties and more distant background galaxies. Strong lensing produces multiple images, arcs, and rings of background galaxies, while weak lensing creates subtle distortions in background galaxy shapes that reveal cluster mass distributions. The Coma cluster, located roughly 320 million light-years away, contains over 1,000 identified galaxies within a volume approximately 20 million light-years across. This rich cluster provided early evidence for dark matter, when Fritz Zwicky calculated that visible galaxies alone could not provide sufficient gravitational binding to prevent cluster dispersal given the observed galaxy velocities. Galaxy cluster formation occurs through hierarchical assembly as smaller galaxy groups merge under gravitational attraction over billions of years. During major merger events, clusters experience violent relaxation processes that mix member galaxies, heat the intracluster medium, and trigger shock waves propagating throughout the cluster volume. The Perseus cluster demonstrates active galactic nucleus feedback on cluster scales through radio bubbles inflated by the central black hole in Perseus A, NGC 1275. These bubbles displace intracluster gas while preventing excessive cooling and star formation, illustrating how supermassive black holes regulate cluster evolution across cosmic time. Cluster galaxies exhibit different properties compared to field galaxies due to environmental effects operating within the harsh cluster environment. Ram pressure stripping removes gas from spiral galaxies as they move through the hot intra-cluster medium, while tidal interactions with other cluster members can trigger starbursts or completely disrupt smaller galaxies. The morphology density relation shows that elliptical and lenticular galaxies dominate cluster cores, while spiral galaxies become more common toward cluster outskirts. This trend reflects how environmental processes transform galaxy properties over cosmic time, converting gas-rich spirals into gas-poor early-type systems. Galaxy cluster velocity dispersions, typically ranging from 500 to 1,500 kilometers per second, provide direct measurements of cluster mass through the virial theorem. These large velocity dispersions indicate enormous cluster masses, while demonstrating that individual galaxies move at speeds far exceeding galactic escape velocities, requiring dark matter to maintain cluster gravitational binding. The Hydra Centaurus supercluster, also known as the Great Attractor, exerts gravitational influence on our local group and surrounding galaxy clusters, despite lying roughly 250 million light-years away. This massive structure contains tens of thousands of galaxies and demonstrates how large-scale gravitational flows shape cosmic dynamics across hundreds of millions of light-years. Superclusters represent the next level of cosmic organization, containing multiple galaxy clusters and groups connected by filamentary structures spanning 100 to 500 million light-years. The Virgo supercluster, containing our local group along with the Virgo cluster and dozens of smaller galaxy groups, spans roughly 110 million light-years and contains an estimated 100 to 200 galaxy groups. The Laniakea supercluster, defined through galaxy velocity flow patterns, encompasses the Virgo supercluster, along with several neighboring superclusters, including Hydra Centaurus, Pavo Indus, and southern superclusters. This enormous structure spans approximately 520 million light-years and contains roughly 100,000 galaxies with a total mass around 100,000 times that of the Milky Way. Supercluster boundaries are defined by watersheds in the cosmic velocity field, regions where galaxy motions change direction due to competing gravitational influences from neighboring massive structures. These boundaries shift over cosmic time as large-scale structure continues evolving under gravitational attraction and cosmic expansion. The cosmic web emerges clearly when mapping supercluster distributions across large volumes of space. Superclusters align along filamentary structures separated by vast cosmic voids, creating a foam-like pattern that represents the largest-scale organization of matter in the universe. Galaxy cluster evolution proceeds through continuous accretion of smaller structures, with most present-day rich clusters having assembled their current masses within the past 10 billion years. Cluster archaeology techniques using galaxy stellar populations and intra-cluster light reveal the assembly histories of these massive structures. The cluster void contrast demonstrates how matter distribution varies dramatically across cosmic scales. While galaxy clusters reach densities 1,000 times the cosmic average, cosmic voids exhibit densities 10 to 20% below average, creating the largest density contrasts observed in the universe. X-ray observations reveal complex temperature and density structures within galaxy clusters, including cool cores, merger shocks, and cavities inflated by active galactic nuclei. These features provide diagnostics of cluster physics while revealing ongoing dynamical processes within seemingly relaxed systems. The Sunyaev-Zeldovich effect enables cluster detection through cosmic microwave background distortions caused by hot intra-cluster gas. This technique proves particularly valuable for finding high redshift clusters and measuring cluster masses independent of galaxy population properties. Cluster cosmology utilizes the abundance and redshift distribution of galaxy clusters to constrain fundamental cosmological parameters, including matter density, dark energy properties, and primordial fluctuation amplitudes. Clusters serve as massive probes of cosmic structure formation and the growth of density perturbations over cosmic time. The transition from bound cluster scales to unbound supercluster scales marks a fundamental shift in cosmic dynamics. While galaxy clusters resist cosmic expansion through gravitational binding, superclusters and larger structures participate in Hubble expansion, with constituent clusters gradually separating over cosmic time. Dark energy's influence becomes apparent on supercluster scales, where its repulsive effects compete with gravitational attraction from matter concentrations. The accelerating cosmic expansion driven by dark energy prevents new large-scale structure formation while gradually weakening existing gravitational associations. From these cosmic metropolises of galaxies, our journey now ventures into the realm of the cosmic web itself, the largest scale structure in the universe, where filaments of galaxies stretch across billions of light years, separated by enormous voids that dwarf even the galaxy superclusters we have just explored. The universe exhibits structure on scales so vast that entire galaxy superclusters appear as mere nodes in a cosmic network spanning billions of light years. This cosmic web represents the ultimate expression of gravitational organization, where dark matter filaments stretching across cosmic distances channel ordinary matter into the galaxies and galaxy clusters we observe today. Mapping the cosmic web requires surveying millions of galaxies across enormous volumes of space to reveal the underlying scaffold of dark matter that shaped cosmic structure formation. The Sloan Digital Sky Survey and similar projects have mapped galaxy distributions out to distances exceeding 2 billion light-years, revealing a universe filled with interconnected filaments, massive walls, and enormous voids. The cosmic web's architecture resembles a three-dimensional spider web or bath foam, with dense filaments intersecting at nodes where galaxy clusters form, while vast regions called cosmic voids contain relatively few galaxies. This structure emerged from tiny density fluctuations in the early universe that grew through gravitational amplification over billions of years of cosmic evolution. Cosmic filaments represent the backbone of large-scale structure, containing roughly 60% of all matter in the universe, despite occupying only 5 to 10% of cosmic volume. These structures span hundreds of millions of light-years while maintaining widths of 10 to 20 million light-years, proportions resembling cosmic highways connecting galaxy cluster intersections. The Sloan Great Wall exemplifies cosmic-scale structure, stretching approximately 1.37 billion light-years across, while maintaining relatively narrow width and thickness. This enormous wall contains thousands of galaxies arranged in a sheet-like configuration that represents one of the largest coherent structures ever observed in the universe. Even larger structures challenge our understanding of cosmic homogeneity. The Hercules-Corona Borealis Great Wall spans roughly 10 billion light-years, approximately 10% of the observable universe's diameter, while containing hundreds of thousands of galaxies organized into an enormous wall-like structure. Some astronomers question whether such large structures can form within standard cosmological models. Cosmic voids occupy the majority of universal volume while containing less than 10% of all galaxies. The Bootes void, spanning approximately 330 million light-years in diameter, contains only about 60 known galaxies, a density roughly 10 times lower than typical cosmic regions. These empty regions demonstrate how matter congregated along filaments during structure formation, leaving vast volumes nearly devoid of luminous matter. The local void, lying adjacent to our local group, spans roughly 150 million light-years, while containing unusually few galaxies. Our location near this void's edge partially explains our galaxy's relatively isolated environment compared to galaxies residing within rich clusters or along major filaments. Void galaxies exhibit different properties compared to those in denser environments, often maintaining active star formation and lower metallicities due to reduced interactions and mergers. These pristine environments preserve records of galaxy evolution under conditions of minimal external influence, providing insights into intrinsic galactic evolution processes. The cosmic web's formation resulted from gravitational amplification of quantum fluctuations generated during cosmic inflation in the universe's first fraction of a second. These primordial density perturbations, imprinted in the cosmic microwave background radiation, provided the seeds from which all cosmic structure ultimately developed. Dark matter's role in cosmic web formation proves crucial because it interacts only gravitationally, enabling it to begin clustering earlier than ordinary matter that remained coupled to radiation until cosmic recombination roughly 380,000 years after the Big Bang. Dark matter scaffolding guided subsequent galaxy formation along pre-existing filamentary structures. Computer simulations of cosmic structure formation, such as the Millennium Simulation and Illustris project, reproduce observed cosmic web properties through gravitational evolution of dark matter particles within expanding cosmological volumes. These simulations demonstrate how simple gravitational physics can generate the complex hierarchical structure observed throughout the universe. Baryon acoustic oscillations, subtle patterns in galaxy clustering reflecting sound waves in the early universe, provide standard rulers for measuring cosmic distances and testing cosmological models. These oscillations appear as preferred separations of roughly 150 megaparsecs, 490 million light-years, in galaxy correlation functions, enabling precision cosmology through large-scale structure surveys. The cosmic web influences galaxy formation and evolution through environmental effects, operating across enormous scales. Galaxies forming within massive filaments experience different evolutionary pathways compared to those in void environments, demonstrating how large-scale structure shapes galactic properties over cosmic time. Cosmic web dynamics involve complex interplay between gravitational collapse, cosmic expansion, and dark energy effects. While filaments continue growing through gravitational accretion, dark energy's repulsive influence prevents further structure formation on the largest scales while gradually weakening existing gravitational associations. The observable cosmic web extends to redshifts where galaxies become too faint for detection with current telescopes, but indirect methods reveal structure formation occurring at even higher redshifts. Lyman alpha forest observations using distant quasars as background sources trace the cosmic web's hydrogen component back to redshifts exceeding 6, corresponding to when the universe was less than 1 billion years old. Cosmic web mapping reveals that our local group resides within a relatively low-density region between major filaments, explaining our galaxy's isolation from rich cluster environments. This location may have provided stable conditions enabling complex biological evolution on Earth by avoiding environmental hazards associated with denser cosmic regions. The intergalactic medium-filling space between galaxies contains roughly half of all ordinary matter in the universe, distributed primarily within cosmic web filaments at extremely low densities. This material, heated to temperatures around 100,000 to 10 million degrees Celsius, remains largely invisible to direct observation, but reveals itself through absorption lines in quasar spectra. Cosmic web connectivity determines how efficiently galaxies can accrete gas for ongoing star formation. Galaxies at filament intersections receive steady gas supplies along multiple channels, while those in void environments experience gas starvation that eventually terminates star formation and galactic evolution. The transition from cosmic web scales to the observable universe as a whole represents our final step in this journey through cosmic scales. The web-like structure we observe represents only a fraction of potentially infinite cosmic structure extending far beyond our observational horizon, raising profound questions about the universe's ultimate size and nature. Measuring cosmic web properties requires techniques spanning the entire electromagnetic spectrum plus gravitational wave astronomy and high-energy particle detection. Multi-wavelength surveys reveal different components of the cosmic web, from star-forming galaxies visible in optical light to hot gas detectable in X-rays, and dark matter mappable through gravitational lensing. The cosmic web demonstrates how simple physical laws, gravity, thermodynamics, quantum mechanics, can generate extraordinary complexity through 13.8 billion years of cosmic evolution. From nearly uniform initial conditions, gravitational instability created the hierarchical structure culminating in the cosmic web's magnificent architecture. Understanding the cosmic web provides essential context for interpreting observations of distant galaxies, galaxy evolution, and the cosmological parameters governing universal expansion and structure formation. The web represents the universe's attempt to organize matter gravitationally, while cosmic expansion works to separate material across ever-increasing distances. From this grandest scale of cosmic structure, we now approach our journey's culmination by examining the observable universe as a whole, the complete sphere of space and time, accessible to astronomical observation, encompassing every galaxy, every star, every atom that light has had time to reach us since the universe began. The observable universe encompasses everything that light has had sufficient time to reach Earth since the universe began 13.8 billion years ago. Yet, due to cosmic expansion during light's travel time, the most distant observable objects now lie approximately 46.5 billion light-years away, creating a cosmic horizon that defines the ultimate boundary of human knowledge about physical reality. This spherical region, centered on Earth, contains roughly 2 trillion galaxies, each hosting tens to hundreds of billions of stars. The total number of stars within the observable universe approaches 10 to the 24th, a quantity exceeding the number of grains of sand on all Earth's beaches by factors of millions. Every point of light visible in the night sky represents just the tiniest fraction of this cosmic stellar population. Understanding cosmic horizons requires grappling with the relationship between distance and time in an expanding universe. When we observe a galaxy 10 billion light-years away, we see it as it existed 10 billion years ago, when the universe was only 3.8 billion years old. The most distant galaxies observable today appear as they were when the universe was less than 500 million years old. Infant galaxies forming their first generations of stars. The cosmic microwave background radiation, observable at a redshift of approximately 1100, represents the most distant signal accessible to electromagnetic astronomy. This radiation originated roughly 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms, making the universe transparent to light for the first time. The surface of last scattering, the spherical shell from which cosmic microwave background radiation originates, now lies roughly 46 billion light-years away, due to cosmic expansion during the 13.8 billion years since recombination. This represents our ultimate electromagnetic horizon. No information from earlier epochs can reach us through photons because the universe remained opaque to electromagnetic radiation. The observable universe's radius of 46.5 billion light-years creates a volume of approximately 4 times 10 to the 32nd cubic meters, containing roughly 10 to the 53rd kilograms of matter. This represents only the portion of the universe accessible to observation. The entire universe may extend infinitely beyond our cosmic horizon, or terminate at distances we can never observe directly. Galaxy number density averages roughly 0.2 galaxies per cubic megaparsec throughout the observable universe, though this distribution varies dramatically due to cosmic web structure. Dense regions like galaxy clusters contain hundreds of galaxies per cubic megaparsec, while cosmic voids exhibit densities 10 times lower than average. The Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec, quantifies the rate of cosmic expansion and determines the relationship between galaxy distances and recession velocities. This fundamental parameter sets the scale of the observable universe while revealing that space itself expands, carrying distant galaxies away from us at velocities that can exceed the speed of light. Cosmic expansion affects our observations in profound ways through cosmological redshift, which stretches electromagnetic radiation to longer wavelengths during its journey across expanding space. Galaxy spectra shift toward the red end of the spectrum by amounts proportional to their distances, enabling astronomers to measure both distances and cosmic expansion history simultaneously. The most distant galaxies currently observable exhibit redshifts exceeding 10, meaning their light has been stretched to wavelengths more than 10 times longer than when originally emitted. These ancient galaxies appear at infrared wavelengths despite emitting primarily ultraviolet radiation when their light began its journey toward Earth. Dark energy comprises roughly 68% of the universe's total energy density, while remaining completely mysterious in its fundamental nature. This enigmatic component drives accelerating cosmic expansion, overcoming gravitational deceleration that dominated early cosmic evolution. Dark energy's discovery through distant supernova observations revolutionized cosmology while raising profound questions about space-time's ultimate nature. Dark matter accounts for approximately 27% of cosmic energy density, outweighing ordinary matter by factors of 5 to 1 throughout the universe. Despite comprising the majority of gravitating matter, dark matter remains undetected by direct laboratory experiments, revealing itself only through gravitational effects on visible matter and electromagnetic radiation. Ordinary matter, everything composed of atoms and their constituent particles, represents merely 5% of the universe's total energy density. This includes all stars, planets, gas clouds, and living organisms throughout the observable universe. The remarkable fact that atomic matter plays such a minor role in cosmic energy balance emphasizes how much we still don't understand about reality's fundamental nature. The cosmic inventory reveals a universe dominated by unknown components whose properties remain largely mysterious despite decades of intensive research. Dark energy and dark matter together comprise 95% of cosmic energy density, relegating the familiar world of atoms to minority status in the cosmic census. Primordial nucleosynthesis during the universe's first few minutes created the light elements, hydrogen, helium, and traces of lithium, that provided raw material for first-generation star formation. These primordial abundances, predicted by Big Bang theory and confirmed by astronomical observations, provide crucial evidence supporting our understanding of cosmic origins. The first stars, forming roughly 100 to 200 million years after the Big Bang, consisted almost entirely of hydrogen and helium because heavier elements had not yet been synthesized through stellar nucleosynthesis. These massive, short-lived stars enriched the interstellar medium with carbon, oxygen, silicon, iron, and other heavy elements essential for planet formation and biological chemistry. Cosmic star formation history peaked roughly 10 billion years ago, when the universe was 3.8 billion years old, then declined steadily as gas supplies were consumed or heated by feedback processes. The current star formation rate represents only a few percent of the peak rate, indicating that the universe's stellar production has passed its maximum activity phase. Galaxy formation and evolution proceeded through hierarchical assembly as smaller structures merged to form progressively larger systems. The most massive galaxies visible today assembled their stellar masses primarily during the first few billion years after the Big Bang, while smaller galaxies continued forming stars over longer timescales. Quasars, supermassive black holes accreting material at enormous rates, dominated cosmic energy output during the universe's first few billion years before declining dramatically as black hole feeding rates decreased. These brilliant objects, visible across the entire observable universe, provide probes of cosmic evolution and structure formation throughout cosmic history. The reionization epoch, occurring roughly 150 million to 1 billion years after the Big Bang, transformed the universe from neutral to ionized, as the first stars and black holes produced sufficient ultraviolet radiation to ionize intergalactic hydrogen. This phase transition fundamentally altered cosmic evolution by affecting subsequent star formation and galaxy assembly processes. Type Ia supernovae serve as standard candles for measuring cosmic distances and expansion history because their peak luminosities remain remarkably consistent regardless of host galaxy properties or cosmic epoch. Observations of distant supernovae revealed cosmic acceleration and led to dark energy's discovery, demonstrating how stellar explosions can illuminate universal properties. The cosmic distance ladder combines multiple measurement techniques to establish distances throughout the observable universe, from parallax measurements of nearby stars to surface brightness fluctuations in distant galaxy clusters. Each technique calibrates the next, creating a chain of measurements extending from solar system scales to cosmic horizons. Cosmic time corresponds differently to observer time due to relativistic effects in an expanding universe. Events that appear simultaneous to distant observers occurred at different cosmic times as measured by local clocks, complicating attempts to establish universal simultaneity across cosmic distances. The observable universe continues expanding, with our cosmic horizon growing by approximately 1 light-year per year as light from previously unobservable regions reaches Earth for the first time. However, cosmic acceleration means that galaxies beyond certain distances will eventually disappear from view as space expansion carries them beyond our future light cone. Future observations will push deeper into cosmic history through increasingly powerful telescopes capable of detecting fainter and more distant objects. The James Webb Space Telescope and its successors will reveal galaxy formation processes occurring within the first few 100 million years after the Big Bang, approaching the limits of electromagnetic observability. The observable universe represents humanity's ultimate laboratory for testing physical theories under extreme conditions impossible to replicate terrestrially. Cosmic observations probe matter behavior at the highest energies, strongest gravitational fields, largest scales, and earliest times accessible to scientific investigation. From this cosmic perspective encompassing everything observable, we now contemplate what may lie beyond our horizon, regions of space and time that remain forever hidden from direct observation, yet may hold keys to understanding reality's ultimate nature and extent. At the edge of everything we can ever hope to observe lies the most profound mystery in cosmology: what exists beyond our cosmic horizon. The observable universe, vast as it appears, may represent an infinitesimally small fraction of a cosmos that extends without limit, containing regions we will never see and phenomena we can never directly study. Current cosmological models suggest the entire universe could be vastly larger than the observable portion, perhaps infinitely so. If cosmic inflation stretched space exponentially during the universe's first fraction of a second, then regions now separated by distances exceeding 10 to the 23rd times the observable universe's diameter may exist, each containing their own cosmic web of galaxies, stars, and potentially life. The concept of cosmic inflation proposes that space itself underwent exponential expansion during approximately 10 to the negative 36 to 10 to the negative 32 seconds after the Big Bang, increasing the universe's size by factors exceeding 10 to the 26 in this brief interval. If inflation occurred, then the observable universe represents merely one small patch of a vastly larger cosmic expanse, most of which remains forever beyond our observational reach. Different inflationary scenarios predict different ultimate sizes for the complete universe. Conservative estimates suggest the entire cosmos could be at least 10 to the 23 times larger than the observable universe, while more speculative models allow for infinite size. In either case, the portion accessible to human observation becomes negligibly small compared to the universe's true extent. Eternal inflation theories propose that cosmic inflation never completely ended, but continues in most regions of space, while occasionally creating pocket universes like our own observable cosmos. This process could generate an infinite multiverse containing countless separate domains, each with potentially different physical laws, fundamental constants, and evolutionary histories. The multiverse concept raises profound questions about the nature of physical reality and the meaning of scientific observation. If infinite universes exist with every possible combination of physical properties, then our universe's apparent fine-tuning for life becomes a selection effect rather than evidence for design. We observe suitable conditions because unsuitable universes cannot support observers. Quantum mechanics adds additional layers of complexity through the many worlds interpretation, which suggests that quantum measurements create branching realities where all possible outcomes occur in parallel universes. If correct, this interpretation implies that countless versions of cosmic history play out simultaneously, including versions where Earth never formed or life never evolved. String theory predicts the existence of additional spatial dimensions beyond the three we observe directly, possibly compactified at scales too small for detection or extending infinitely in directions perpendicular to our familiar three-dimensional space. These extra dimensions could contain entire universes separated from ours by microscopic distances in higher dimensional space. Brain cosmology scenarios propose that our universe exists as a three-dimensional membrane floating in higher dimensional space, potentially alongside other brain universes separated by tiny distances in extra dimensions. Gravitational effects might leak between nearby brains, offering possible experimental signatures of parallel universes. The anthropic principle attempts to explain our universe's properties by arguing that physical constants must fall within narrow ranges compatible with life and intelligence, because only such universes can contain observers capable of measuring these constants. This reasoning suggests that our cosmic parameters reflect observational selection rather than fundamental physics. However, the anthropic principle remains controversial because it appears to abandon traditional scientific methodology by invoking unobservable entities to explain observed phenomena. Many physicists prefer to seek fundamental theories that predict our universe's properties without invoking observer selection effects or infinite multiverses. Dark energy's nature remains completely mysterious, despite comprising roughly 68% of cosmic energy density. This unknown component could represent a cosmological constant built into spacetime's fundamental structure, or it might indicate modifications to general relativity on cosmic scales. Or it could result from interactions between our universe and external structures in higher dimensional space. The ultimate fate of our observable universe depends critically on dark energy's long-term behavior. If dark energy remains constant, cosmic expansion will continue accelerating forever, eventually isolating every galaxy within its own cosmic horizon as space expansion carries distant objects beyond the speed of light relative to local observers. Heat death scenarios predict that continued cosmic expansion will eventually spread matter and energy so thinly that temperature differences disappear throughout space, ending all thermodynamic processes and reducing the universe to maximum entropy equilibrium. This ultimate fate could occur within 10 to the 100 years if current expansion trends continue indefinitely. Alternative scenarios include big rip cosmologies, where dark energy strengthens over time, eventually overcoming all fundamental forces and tearing apart atoms themselves within finite time. Cyclic universe models propose that cosmic expansion might reverse, leading to Big Crunch collapse, followed by renewed Big Bang expansion in endless cycles. The information paradox questions whether information can be truly destroyed when black holes evaporate through Hawking radiation, or when cosmic expansion carries matter beyond event horizons. Resolving this paradox may require new physics that fundamentally alters our understanding of spacetime, quantum mechanics, or thermodynamics. Cosmic censorship hypotheses suggest that nature prevents naked singularities from forming, always clothing them within event horizons that hide their extreme physics from external observers. If cosmic censorship fails in some circumstances, observers might directly witness regions where general relativity breaks down completely. The measurement problem in quantum mechanics becomes especially acute on cosmic scales, where decoherence mechanisms may prove insufficient to explain the classical behavior of large-scale structure. Understanding how quantum superposition transitions to classical definiteness in cosmic contexts remains an open, fundamental question. Consciousness and observation play puzzling roles in quantum mechanics, raising questions about whether intelligent observers are necessary for wave function collapse, or whether purely physical processes suffice. If observers are required, then the emergence of consciousness in the universe takes on cosmological significance for determining physical reality's structure. The fine-tuning problem highlights how many fundamental constants appear precisely calibrated to enable complex structure formation and biological evolution. Small changes in particle masses, force strengths, or cosmological parameters would prevent stars, planets, or life from forming, suggesting either remarkable coincidence or deeper organizing principles. Attempts to solve fine-tuning through multiverse theories remain controversial because they invoke unobservable entities while potentially undermining scientific methodology's predictive power. If all possible universes exist somewhere, then any observation becomes consistent with theory, eliminating empirical constraints on theoretical speculation. Mathematical Platonism proposes that mathematical structures exist independently of physical reality, with our universe representing one particular mathematical object among infinitely many possible structures. This perspective suggests that the deepest level of reality consists of abstract mathematical relationships rather than concrete physical substances. The simulation hypothesis speculates that our entire observable universe might exist as a computational process within some vast computer system operated by advanced civilizations. If computational power continues growing exponentially, future civilizations might simulate countless universes containing conscious beings who experience reality as genuine physical existence. Digital physics theories propose that space-time and matter emerge from underlying discrete computational processes operating at the Planck scale. If reality consists fundamentally of information processing rather than continuous physical fields, then our universe might represent a natural computational process rather than artificial simulation. The holographic principle suggests that all information contained within any volume of space can be encoded on that volume's boundary surface, implying that three-dimensional reality might emerge from more fundamental two-dimensional information structures. This principle, derived from black hole physics, could indicate that dimensional perception represents an illusion masking reality's true lower-dimensional nature. Scientific methodology faces fundamental limitations when attempting to study regions beyond the observable universe or phenomena that leave no empirical signatures. How can we distinguish between untestable speculation and legitimate scientific hypothesis when addressing questions about reality's ultimate nature and extent? The cosmic perspective transforms human significance by revealing our species as temporary arrangements of matter that emerged from cosmic evolution on an unremarkable planet, orbiting an ordinary star in a typical galaxy among trillions of galaxies within an possibly infinite cosmos. Yet this same perspective demonstrates that through scientific observation and reasoning, matter has organized itself sufficiently to comprehend its own cosmic context. Perhaps the most remarkable fact about the universe is that it contains regions, like the solar system where Earth resides, where matter has complexified sufficiently to generate conscious observers capable of understanding cosmic evolution from quantum scales to cosmic horizons. Through human scientific investigation, the universe has developed the capacity for self-awareness and self-study. Our journey from human scale to cosmic horizons reveals the extraordinary range of organization exhibited by matter and energy throughout the accessible cosmos. From the quantum foam underlying space-time to the vast cosmic web spanning billions of light-years, every scale reveals new phenomena while contributing to the hierarchical structure that enables complexity to emerge from simple components. The universe's true extent may forever remain mysterious, lying beyond the fundamental limits imposed by light speed and cosmic expansion on human observation. Yet within our observable cosmic domain, we have discovered a universe of stunning beauty, complexity, and mystery that continues revealing new wonders with each advance in observational capability and theoretical understanding. Whether the cosmos extends infinitely beyond our horizon, whether other universes exist in parallel dimensions, whether reality consists ultimately of mathematics or information or something entirely beyond current conception, these questions may transcend human cognitive capabilities while inspiring continued scientific exploration of the observable universe's remarkable properties and evolutionary history. From this ultimate cosmic perspective, we return to Earth, to human scale, to the remarkable fact that the universe has organized matter in at least one location sufficiently to generate consciousness capable of contemplating its own cosmic context. We are the universe becoming aware of itself, a remarkable achievement that may be rare or common throughout the cosmos, but which represents the culmination of 13.8 billion years of cosmic evolution, producing complexity from simplicity through the action of natural laws operating across every scale from quantum to cosmic. We have traversed 35 orders of magnitude from the 1.7-meter human form to the 46.5 billion light-year observable universe. This journey reveals that we exist at a unique position in the cosmic hierarchy, large enough to manipulate individual atoms through technology, small enough to study distant galaxies through telescopes, and complex enough to comprehend our own cosmic context through scientific reasoning. The universe exhibits organization across every scale we have explored, from quantum fields to cosmic web filaments, suggesting that complexity and structure represent fundamental features of physical reality rather than rare exceptions. Through 13.8 billion years of cosmic evolution, matter has organized itself into increasingly complex arrangements, culminating in conscious observers capable of understanding their own cosmic origins and context. Every human being represents the universe achieving self-awareness through biological evolution on at least one planet, orbiting one star among hundreds of billions in our galaxy, among trillions of galaxies within the observable cosmos. We are made of stellar material organized through cosmic processes into forms capable of contemplating cosmic scales from quantum foam to infinite space. This cosmic perspective simultaneously humbles and elevates human significance. We occupy an infinitesimal fraction of cosmic space and time, yet we represent remarkable achievements in cosmic organization, matter arranged with sufficient complexity to generate consciousness, curiosity, and comprehension of scales spanning dozens of orders of magnitude beyond direct sensory experience. The hidden world smaller than us and the giant universe beyond us together reveal that reality operates according to natural laws that transcend human intuition while remaining accessible to human scientific investigation. From quantum mechanics to cosmic expansion, from stellar nucleosynthesis to biological evolution, we have discovered our deep connections to every scale and epoch of cosmic history. Understanding cosmic scale provides essential context for addressing humanity's greatest challenges and opportunities. Climate change, resource management, space exploration, artificial intelligence, and biotechnology all require thinking across multiple scales while recognizing our species' position within the vast cosmic context that ultimately determines our existence and future possibilities. The journey from human to cosmic scales continues through advancing technology, expanding consciousness, and deepening scientific understanding. Each generation discovers new scales, new phenomena, and new connections between the quantum and cosmic realms that constitute our remarkable universe. We are the cosmos contemplating itself, a profound responsibility and extraordinary opportunity that defines humanity's unique role in the ongoing evolution of complexity, consciousness, and cosmic understanding.